Hi, my name is Gunnar O'Connor. I'm a senior product development engineer at Latent Heat Solutions. I'm giving this presentation on critical factors of battery pack design failures from data to testing with our Director of Product Development Engineering, Joe Kelly. He'll cover the thermal management side of the presentation, and I'm going to start the presentation out with thermal runaway protection. Just a little background on who we are. We started as Outlast Technologies in the 1990s, and then we went into textiles with that technology, and eventually around 2012, we were acquired by Coors Tech and went into industrial applications such as battery packs. We've been in that space ever since then, and recently in October 2020, we were acquired by another thermal management and thermal monitoring company, group of companies, the Cavu Group. So a little overview of what we're going to go through here. So first, we're going to break this into two parts. It'll be a thermal runaway section and a thermal management section. So we'll give a bit of background on thermal runaway concerns, and then we'll go into proposed solutions to address those concerns, and then give supporting empirical data and test results, as well as some demo videos supporting that. And then we'll do the same with thermal management, addressing the background, proposed solutions, examples, and closing with a conclusion. So to give a bit of background on thermal runaway and cell ejecta, when lithium-ion cells reach a high enough temperature or are damaged in such a way and then reach a high enough temperature, they will continue increasing in temperature until they eject their electrolyte and core materials, usually resulting in a fire upwards of 500, 600, 700 degrees Celsius, which can damage other pack components, other cells, causing thermal propagation, and so on. And this is the behavior of the cell is very dependent on the cell chemistry, the cell manufacturer, how it's arranged in the pack, whether it's pointing at other cells in the pack, whether it doesn't really have much room for the pressure to get out, as well as the power and energy densities of the cells themselves and the whole pack. And upwards of 80% of the energy can be ejected from the cell during this event. So that 80% of the thermal energy can go directly into another important part of the pack. If it's a pack that's located on a person, into the person, or into adjacent cells and causing a larger fireball and a lot more damage. So breaking cell ejecta out into a few different categories. We have ejecta coming out of the positive terminal, which ejects just the way it should through the vents that are designed into the cell. We have in newer cells an etched circle on the bottom that acts as a rear or a negative terminal vent that will eject gases and components out the back of the cell as well, usually both the front and back. And then we can also have the entire jelly roll ejected out the positive terminal. Instead of just venting gases and flame, it'll eject a bunch of shrapnel that can go into almost act as a nail penetration event or a crushing event for another cell. And the worst of all that we found has been the side ruptures. So if just the can peels open and ejects all of its components at once into an adjacent cell that for most pack designers is 1.5 to 2 millimeters away. A lot of these events are stopped by pressure relief, PTCs, CIDs to stop the event before it happens. But in terms of damaging abuse events, such as that we use like nail penetration to test, or maybe there's a car accident, PTCs and CIDs are not going to stop that. Here's an image from a NASA presentation. They had a bomb calorimeter and they measured how much energy comes out of the positive terminal, negative terminal, and sidewalls. And they did a bunch of different cells. I pulled this one just as an example. This is an LG MJ1 cell, and it shows about 74, 75% of the energy is coming out of the positive terminal, just as it's designed to with the vents ejecting straight out. Then in terms of more heat coming out of the sides, radiating out of the sides, not necessarily ejecting out of the sides, about 21, 23% there. And then a much smaller percent is about 3.6 comes out of the rear terminal, and that's because this one doesn't have a terminal vent. And with cells with terminal vents, we see 15–20% of the energy coming out there. So in terms of our proposed solution, we like to address 3 different aspects here for the design and implementation of materials or solutions. First is capturing and converting the thermal energy. So placing high latent heat materials at venting points, maybe just the positive terminal, maybe just the sidewalls, or maybe all parts of the cell that you can cover. This material then vaporizes into a non-combustible vapor. That phase transition absorbs a considerable amount of energy that is not going to the rest of the pack. 2, very importantly, is quenching and extinguishing further flaming to not add continued heat into the system, which will just continue to heat up adjacent cells beyond the heat from the trigger cell. And 3, and something that we discovered much later in the process, was blocking and deflecting ejected particles. So you can put all these materials that absorb the thermal energy and quench the flaming, but if the cell ejects right into an adjacent cell, that cell can go within a second, and there's not much you can do to stop it unless you have a barrier material, and this barrier material can take the form of metal sheet, ceramic plates, or even thermoplastics in a shape of a matrix to contain it. So in terms of LHS's proposed solution for this, it takes the form of the XTS product. So this is a non-traditional PCM gel with an extremely high latent heat of about 2,000 joules per gram inside an aluminized laminate pouch that is designed specifically for each customer to conform to their pack geometry. When the temperature of the cell gets above 105 degrees Celsius, it then vaporizes and then begins absorbing that thermal energy off. So when thermal runaway occurs, the pouch will rupture, and then the gel will be able to access the hot thermal, or the hot trigger cell. And then in addition to this, we also have a sort of a sidekick solution here with the XTS SC1 composite, and we like to use this for side rupture prone cells, one of them being the Samsung 30Q. You can see in the image to the left, that is the trigger cell that we nail penetrated. When we removed it from the matrix, the matrix had completely contained the side rupture that would have ejected right into an adjacent cell. So I'm going to show 2 tests that we did for some customers. Just to go over the testing methodology, we wire all of our cells with omega K-type thermocouples, and then we will initiate thermal runaway through either nail penetration at 8 centimeters per second, or hot wire, which, depending on customer requirements, about 5 to 10 degrees C per minute ramp rate. Less commonly, we'll do an overcharge or short circuit, but most people are interested in hot wire nail penetration. All the tests are safely performed in a ventilated fireproof chamber behind several layers of plexiglass, so that customers can come in and watch it, and we as the testers can watch at a safe distance. And there's a camera on the inside, and there's a camera on the outside. And then at the end of it, we'll put all this into a report with post-mortem tests and setup pictures, as well as data analysis to deliver to the customer. So this first test that we did was using LG MH1 18650 cells in a 2S16P configuration. We put pouches on all sides of the 2 packs. There were 2 modules. The trigger module was directly facing the adjacent module, so in a worst case scenario, it'll just eject right into it. We have a lot of material here, and we also put Insulfrax barriers between every cell, so we were thinking to insulate any sort of cell-to-cell thermal transfer there. There's 6 thermocouples on each module, so not all the cells are wired there. And then these modules are put into a larger enclosure with a bit of headspace per the customer's request, and then it was put into an even thicker, more durable container, so it didn't just blow apart during the thermal runaway. So we have that first cell going, and it was nice big fireball. The flame seems to go out pretty quickly, but evidently there was another cell damage in that first explosion, and then we just have a constant thermal propagation from this point forward. So the data we see here is just showing basically full thermal runaway. So the first pack, immediately several cells go, and then a little bit of burning and the rest of the cells go. And about 800 seconds after the first thermal runaway from the trigger module, the adjacent module then all starts going at once. So we have complete failure of both modules in this case, despite the fact that we had all that material there, we didn't have barrier materials. So just to show you here how we reached that conclusion, analyzing the post-mortem images, we noticed a lot of side ruptures. So multiple cells were having multiple side ruptures. You know, they're coming out the front, the back, the sides. Essentially, that's why you're seeing such quick succession of thermal propagation throughout the cells. So our proposed solution implemented then was the use of barrier materials, which took the form of stainless steel pieces, about 1.5 millimeters thick. We electrically and thermally isolated them with Insulfrax and wrapped with Kapton. And then we isolated every row of 2 cells in each module, and then we put another barrier material between each module to protect from front ejecta, and then if it wanted to eject into the sides. We also bolted it down per customer request, just so it wasn't moving around in the pack. This is the video of that test. So much subtler explosion to start with. Just a puff of gas. So then we have the second cell going there. And still no fire from that. So this is the data from that test. So a lot less chaotic than the first round test that we did there. So in that, we saw cell 1 and 4 fail within about 40 seconds of each other. And the next hottest cell got to about 115 degrees Celsius, which is hotter than it should get, but it wasn't enough in this case to cause it to go to thermal runaway. So the reason why cell 1 and cell 4 went is because in our numbering scheme, cell 1 was the trigger cell and cell 4 was directly below it, separated on either side by the barrier materials. And then we had the XTS pouches to absorb the thermal energy on tops and bottoms, fronts and backs. And then it protected the adjacent module with another piece of metal in front of it there. So this is a really good picture showing how the ejecta hit the pouch, went through the pouch, hit the barrier material, and then kind of just shot straight up with one single path. The whole time it's going through that path, it's losing thermal energy by that phase transition of the XTS gel. This picture shows cell 1 and cell 4 that went to thermal runaway. And if you look on the left, I like this picture a lot because it shows the trigger cell with the wrapper burned off, but the adjacent cells, which are, 1.5 millimeters away, their wrappers are wholly intact. And then the pouch, you can see where the material was used on it. And then on the top and bottom or left and right, there's still material left for it to access in case further cells go to thermal runaway.
Hi, my name is Joe Kelly. I'm Director of Product Development at LHS, and I'd like to take the second half of this presentation to discuss thermal management from a performance perspective. Now, Gunnar talked about thermal runaway and the thermal challenges that are associated with it, and really looking at the factors of battery pack design still apply with respect to cell spacing, cell configurations, additional pack components in terms of cell holders, housings, etc. All which really need to be looked at and really trying to manage the heat from a system to get you the performance that's required. And so during normal charge and discharge, particular pack applications, the self-heating of the pack really provides a lot of that heat, which can be damaging, especially at higher discharge or charge rates. And environmental conditions are also, play a big impact, especially in regional areas where high ambient temperatures need to be managed to properly get the performance required from a particular design or application. And I think most people are aware, that as these particular lithium-ion chemistries see higher temperatures, they have a susceptibility to degrade electrochemically, mechanically over time, which really translates into kind of a loss in capacity or loss in the ability to store charge, which at the end of the day gives you shorter operating times. As these things saturate in heat for long periods of time, you get a reduction in cycle life, reduction in power capabilities, and particularly in larger packs, you'll actually, if you have a large thermal imbalance, particularly between cells within the center of the pack versus the exterior cells, that actually can be a challenge from an electrical standpoint in terms of balancing that pack. And of course, that all feeds back into the safety issue where, if you get a significant amount of degradation, the thermal runaway probability is greatly enhanced. And so being able to manage that effectively, like Gunnar discussed, it is, again, a very high concern for a lot of applications. Now, when we're looking at a thermal management solution, both from a safety perspective as well as from a performance perspective, a lot of times you see in the market, there's just not a one size fit all. A lot of times, when you're looking at thermal management, you want to try to minimize as much heat transfer from a particular cell or module to another. The big delta T's from that event are really hard to manage. And a lot of times what happens is it actually affects detrimentally the operational conditions of a particular pack. Now with the XTS, we've kind of tried to address both aspects of thermal management in terms of safety and performance. So, from a thermal runaway perspective, like Gunnar mentioned, we actually utilize the phase transition of the gel material within these packs and its high thermal dissipation energy to help with thermal runaway. However, we're actually utilizing the high specific heat capacity of the material for more normal charge and discharge type of operations. Again, acting as kind of a heat sink, absorbing heat off the cells, like a traditional PCM, but we're not using any latent heat in this case. And a lot of times, actually, if when you're looking at it from a traditional phase change standpoint, we're actually able to utilize this material pretty effectively, in pretty similar performance characteristics. And the reason for that is we're actually able to make the material into this conformable pouch that helps us really localize the material, so we can ensure good cell surface contact. We're targeting the material in a particular location, so really being more efficient in how we use the material and minimizing any sort of parasitic weight, which is always a concern in a particular battery pack application. Now, the aluminum laminate actually does also have a benefit in that it helps spread the heat across the particular pack, or allows us to more effectively utilize the gel material in there versus, say, a traditional PCM, which is kind of a lower thermal conductivity material. But it still allows us to be electrically insulative, but does provide some more thermal dissipative behavior. And as I mentioned before, we're using this kind of as a heat absorbing material, but we're not using a latent heat. And a lot of times when you're looking at it from a PCM perspective or just a numbers basis, well, you have a certain amount of material that's applied around a cell or a pack, at a specific phase transition band, you actually can absorb a decent amount of heat compared to what we would say, just a specific heat material or a sensible heat material could do. However, a lot of times you're just not utilizing all that material. So you're not utilizing all that mass around a particular heat source. Either that's thermal conductivity, it's just not applied right, etc. And so, for example, this test here, where we have a small 1s4p configuration, using 21700 cells, discharging at 1C at an ambient of 25 degrees C. We're actually applying a traditional PCM versus our XTS in the same weight per cell application under the same conditions. And this particular PCM has a transition band of 30 to 40 degrees C, which is kind of right in line with what we're seeing for the temperatures of this particular pack. And with the XTS being just more effectively utilized, we're actually seeing that the XTS performs better than the PCM. So we're seeing, in terms of a control pack with no thermal management at all, a 21.6% lower delta T on the cells than that control pack versus the PCM, which is only at 13.9%. And again, it's all about effectively utilizing as much material as possible in a particular pack configuration or architecture. Now, if we look at it from just a standpoint of the XTS thermal management, from a passive perspective, this test kind of has an example. Again, we're using 21700 Samsung cells in a 1S3P pack. In this case, we're actually discharging at 1.5C versus the 1C for the previous example, and we're at a cell spacing of 1.9 millimeters. Now, if we're looking at it from a control perspective, without any material in there at all, average cell surface temperatures at the end of discharge get up to 70.1 degrees C. And if you're looking at the XTS, we're actually 18 degrees C lower at the end of discharge, so 51.3 degrees. So a significant drop in temperature, again, because the material is able to absorb that heat off the cell. And when you do that, obviously over time, you're reducing the thermal history or the thermal stress that the XTS control pack has versus just the unthermally managed control example that we show here. And that results in actually a better discharge capacity retention over time. So in this particular case, we're actually seeing a 21% increase in cycle life if we're measuring capacity retention at 80%. So again, that's just because we're helping keep these cells cool, minimizing that stress, which leads to less degradation of the cells over time. Now, of course, like I mentioned before, environmental factors have a big effect in your thermal management solution that you're trying to design to. And a lot of times our customers operate in regional areas where you're up at 35 to 45 degrees C ambient conditions. So in this test, we're actually running a similar small pack, but this is with 18650s. The cell spacing is actually smaller, so we're at 1.5 instead of 1.9. And our discharge rate is a little bit higher as well. So we're at 2.5 C versus 1.5 for the last example. And we're running this test at a 37 degrees C ambient. And we're seeing that we're actually getting still a very good temperature reduction of the XTS material on the particular cells versus a control pack that's not thermally managed. So again, what we're seeing here at the end of discharge is 71.6 degrees C for the control pack versus with XTS, we're at 58.1 degrees, which is about 13.5 degrees C lower. And again, kind of going back to the traditional PCM applications where you really have a challenge in especially higher ambient condition environments of putting a PCM into a particular pack and have it still provide a thermal management benefit, but not have it already be melted into ambient condition. And so this material definitely has a lot less restrictions on that because we don't have a particular temperature band that we need to be in to have it actually activate. But of course, absorbing heat off the cell is not always just the end all be all, right? We have to be able to dissipate that heat away from the pack or from the cell itself throughout the pack or direct it somewhere else. So, from a perspective of this material, if you're looking at kind of the time from discharge down to charge, what we typically do for a lot of these tests is we have a temperature cutoff at 30 degrees C. So after it does a discharge, we allow the cell or the pack to rest until it hits 30 degrees C, and then it will allow it to charge. So in this case, in this particular test, we're actually seeing the XTS ability to recycle, or basically go and do another charge a lot quicker, because we're at a lower cell surface temperature at the end of the discharge, and we're able to thermally dissipate that material effectively. And so this test really highlights that. This is a 21700 test, similar cell spacing, but a discharge at 1C. And again, what we're doing is we're limiting the time to get to the next charge step based on this 30 degrees C cutoff. So with the XTS, we're actually low enough in temperature at the end of the discharge, and we're able to dissipate that heat quickly, that we're actually able to jump right back up into doing a charge, just because we're at a low enough temperature. While with the control, we're actually having to wait about 34 minutes before it gets down to a temperature of 30 degrees C or lower. That allows us to move to the next charge step. So this, of course, obviously has an impact on particular applications such as swappable battery packs, or kind of swappable designs, as well as power tool applications where you want to be able to take a pack kind of right out of the application that you're using it in and charge it up as quick as possible, so that a user can use that again. So again, another big thing to look at when you're looking at thermal management design is kind of what the end goal or end application is being used for. Now, one other thing I want to talk about too is tab cooling. And I know there's been a few things out there regarding kind of the effectiveness of tab cooling. But if you look at it from a perspective of the cell, thermal conductivity, right, is always higher in the Z direction than it is in the X and Y on a particular cell. So, most of the times we have the ability to absorb heat off the cell surfaces, but if we can absorb heat off, the positive and negative tabs, it actually does provide a benefit here. And so for this particular application or example, we have this 5S9P battery pack that actually has our XTS SE1 composite as kind of an inner layer. But what we're doing is we're actually putting our XTS pouches, which Gunnar mentioned before is pretty critical in any sort of ejecta management or ejecta control. And we're putting that directly onto the tabs themselves. And we're actually applying that with a little bit of a thermally conductive transfer adhesive. And what we're actually seeing during the charge, a 1C charge at 18 degrees C ambient, starting at a 36 degrees C condition, that we're actually seeing an average temperature reduction of the cells of about 4 to 5 degrees C, between having pouches on or off the tabs. So to summarize, when developing a thermal management solution, both from a performance and a safety aspect, there's a number of considerations that need to be addressed. Particularly for thermal runaway, there's a number of mechanisms that all need to be managed to provide an optimized solution to mitigate thermal runaway. And these have a big impact on the overall pack design considerations. So our approach with XTS product is to have a customized solution that's able to meet a particular thermal problem, both in safety and performance, but then it can also be tailored to a diversity of pack designs. So while being primarily passive, which is a benefit for smaller format batteries, the XTS product line can be coupled with active cooling methods, particularly for larger format batteries, to provide a synergistic effect where you have the benefit of thermal management from the active cooling system, but then also this passive thermal mitigation for thermal runaway benefit from the XTS. So by having a product that has both properties that allow it to be thermally managed and mitigate thermal runaway, we have an ability to offer a simplification in the design phase for a particular thermal challenge within a customer's pack application. So I invite everyone to go to our website to get more information on our product and the company. And I'd like to now open it up to any questions that you have for me or Gunnar.